Good morning again, everybody. Thanks for signing on and being on time. Y'all are the OGs. How's everybody doing? Did we get a chance to enjoy Friday since Friday was canceled, essentially? That's an actual question. You can respond in the chat if you want to. Very short lived, I agree. It was kind of a little bit last minute, oh yeah, by the way, you can take off Friday. Um, yeah, it's to that part of the semester where it's kind of hard to really take a day off. So I completely understand. I ain't take a day off either. Trying to get ready for baby number 4. Y'all may not remember, but Dr. Hefner's pregnant, due next month. So we have a lot of prep to do. So that's what my weekend was. So if I'm a little bit low energy, that's why. I'm tired. But that's all right. I can still do some chemistry. So sorry, y'all. We still got class. Let's get started on the do now. How would we classify this reaction that we have here? We're mixing 2 aqueous solutions, and we are forming a solid and another aqueous solution. It is indeed a double replacement reaction. So remember, you're taking 2 solutions, which my shorthand for solution is SOLN, and you are creating a solid, which is called a precipitate, and another solution. So that's a double replacement reaction. How many of you were able to balance the equation just by a show of hands, or you can say me? I know we had the exam last week and stuff, but you still had chapter 7 for mastering chemistry. So let's balance that now. Actually, if you got an answer, you can just put in the coefficients that you got separated by a comma. So 5, 2, whatever you got. And if it's a 1, you can put a 1. I'm just curious to see before I start solving it. Alrighty. So we'll keep those answers in mind as we solve this. Oops. So I like to use a table. I look at my reactants and my products, which, just for a refresher, the reactants are on the left-hand side of the arrow. The products are on the right-hand side. Then I go through and write down every element or ion that I see if the ion stays together. So the SO4, the sulfate ion, we see it on both sides. So I can treat it like one unit. The same thing goes for hydroxide. It's on both sides. It's not involved in any other reaction or any other compound. as, broken up as oxygen and hydrogen. So I can keep the hydroxide ion together. When you initially check, we've got the subscript 2, which means that there are 2 potassiums. We've got 1 sulfate, 1 barium, and 2 hydroxides on the reactant side. On the product side, we've got 1 barium, 1 sulfate, 1 potassium, and 1 hydroxide. So clearly we're not balanced. We've got 2 choices. We can either start by balancing the potassium or the hydroxide. Doesn't matter which one in this case. When I solved it, I started with the potassium. You find your lowest common denominator, which in this case is going to be 2. So I'm going to multiply whatever compounds I see on the product side by 2. I remake my chart. And then I see where I am after I made that addition. So I've still got the same thing on the reactant side, but I've changed the products a little bit. So now I have 2 potassiums and 2 hydroxides. Well, it looks like I'm balanced, right? So I've got the same number of elements or ions on both sides. So if this were a multiple choice question where it was asking what are the coefficients of each of these different compounds, you would choose the answer that was that. So everything has a coefficient of 1 except for the potassium hydroxide. So good job for y'all who got it. And if you didn't get it, that's okay. There's still time to practice. Now, I'm not going to ask you to write the chemical equation in words in the chat box. I'll just write down what I wrote. And as long as you have something close to that, then you'll be good. Before I do that, are there any questions about balancing the equation? If not, you can tell me no. All right. So I'm going to go ahead and write out what I wrote for the chemical equation in words. So we're starting with aqueous solutions of potassium sulfate and barium hydroxide. Remember, we have to do the naming, and we also have to include the state of matter. And in this case, the AQ, that means that they're aqueous. Then we have to do that yield sign. So I just wrote our mixed to yield. Keep it simple. Then you write out what your products are. Again, making sure that you're writing the state of matter. And so our products are solid barium sulfate. You could also say barium sulfate precipitate and aqueous potassium hydroxide. So you should have something similar to that. All of the chemical names should be the same. The states of matter should be more or less the same. You could say, again, precipitate instead of solid. It would be the same thing. So is that clear? That's kind of a refresher of a good amount of what we did in Chapter 7. Alrighty. So you'll notice there isn't a Chapter 8 video yet. It's coming. My apologies. Like I said, this weekend was very, very busy. And I knew pretty much no one would watch it because of the exam, especially with the Mastering Chemistry homework and the exam being due on Sunday instead of Friday. So we're going to be working on Chapter 8 for 2 weeks. Normally we take 1 week for a chapter, but the last few chapters, 8, 9, and 10, we're actually going to take a little bit more time because they're math intensive. So the video will be out around midweek, and that will help you with your chapter check-in. The Mastering Chemistry is not due this weekend, so you'll have some time to kind of let it marinate, watch the video, and then we'll come back next week and finish up Chapter 8 and review what we did this week. So the pace is going to be a little bit slower, but this is some of the more difficult material for most students. So just keep that in mind, that just because the pace isn't as fast, we're not going through an entire chapter in a week, that you still need to put in the same amount of time in terms of doing your homework and studying, because the Mastering Chemistry can take a while, particularly if you're not comfortable with doing all the calculations. So I would encourage you to work on the Mastering Chemistry homework for Chapter 8 this week and just do what you understand, even though it's not due until the following week. Alrighty. With that said, we're starting Chapter 8, which is the mole concept. Just by a show of hands, does the word mole mean anything to anybody? Anybody remember it from maybe high school chemistry? Just by a show of hands, or say me. Okay. That's not bad. Ain't but 15 of us in here. So, let's talk about the mole and this concept of Avogadro's number. So Avogadro's a guy, okay, chemist, and this number is named after him for good reason. We're not going to talk about the history, but we are going to talk about the number. So Avogadro's number is simply the number of atoms or molecules in 1 mole of something. So Avogadro's number is 6.02 times 10 to the 23rd. And again, you might see that as particles, atoms, or molecules. So it's a number that you need to become familiar with. I'm not going to give you Avogadro's number for the exam. But if you have a sample of carbon that was 12.01 grams, you would have 6.02 times 10 to the 23rd carbon atoms. So that is what Avogadro's number is based on. The mole is based on Avogadro's number. So we use it as a unit of measure for an amount of a chemical substance. So like I said, 1 mole is equal to Avogadro's number, which is equal to 6.02 times 10 to the 23rd units. That's the take-home point here for both slides. So make sure you get that down in your notebook. We ready to move on? I want to make sure you have time to jot it down if you're writing down notes. So just let me know if you're ready to go or if you need another minute. All right, let's move on. So how do we use this number? We can use Avogadro's number to go from the number of atoms of something to the number of moles, which MOL is the abbreviation for mole or moles. So that's how we can use Avogadro's number to convert the number of atoms of a substance to the number of moles. And I'll give you an example. So we've got a question: how many magnesium atoms are in 1.59 moles of magnesium? The first thing I always do, and this kind of goes back to chapter 2 when we were doing the conversions with the metric conversions and things like that. Always rewrite the question in a simpler form so that you know what unit you have and what unit you're trying to get to. In this case, we're going from moles to some number of atoms. So always make sure that you know what unit you're starting with and what unit you're trying to end with, especially as the questions get more complicated. Then we write out what we know in terms of how to convert. The way that we connect moles and atoms is Avogadro's number. And we can write that as a unit factor. That's one unit factor. Take a second and write down what the other unit factor is. See if you can jar your memory of chapter 2. Hopefully it's not too traumatizing. And you can write in the chat how you get the other conversion factor. You don't have to try to write out the whole conversion factor, but just tell me how you figured it out. Exactly. It's the reciprocal. You just flip it. So now that we've got our unit factors written down, we can figure out which one we want to use. We're starting with moles. And we're trying to get to the number of atoms. Which unit factor should I use, A or B? I should use A because I'm trying to get to atoms. That means I have to cancel out the moles. And if I use that first conversion factor, unit factor, I cancel out the moles and I'm left with magnesium atoms. When you put that into your calculator, you should get this. With sig figs, of course. So you're going to need to remember how to use your calculator using scientific notation, or, being able to put in the exponents, because exponents are back too, y'all. So does that make sense? That's an example of how to convert from moles of a substance to atoms of a substance. At the end, I'm going to give you kind of a cheat sheet for all these different problem types that you can use when you're doing your homework. So we're going to build. This is just the first type of calculation. So let me know if we're good here to move on. Let's do another problem. And so this chapter 8, pretty much the rest of the chapters that we have, 8, 9, and 10, it's going to be a lot of math. So most of our live sessions is going to be working problems. Just giving you the heads up. So make sure you have your calculator, which you probably have your phone, but make sure that you have a calculator. It would be best if you have the calculator you're going to use for the exam so you can get comfortable with it. So now we've got a question. How many moles of tin are in 1.25 times 10 to the 21 atoms of tin? Express your answer in scientific notation. So in this case, we're going in the reverse. We have the number of atoms, and we want the number of moles. What unit factor would I use? And we're choosing from the same two as before. What unit factor would I use to go from atoms to moles? Do I want atoms on top or atoms on the bottom? Yeah, we want those atoms on the bottom so that they cancel this time. So we're going to take the number of atoms we're starting with, and then we're going to say 1 mole of tin on the top and the equivalent number of atoms in the bottom. The atoms cancel. We're left with moles. Your calculator is going to tell you something like that with sig figs. But the question is asking for scientific notation. So take a second and tell me how I would write that answer in scientific notation. Dust off those cobwebs. So we've got a number that is smaller than 1, which means that we're moving our decimal point to the right. That's going to make our coefficient, which is at least 1 and less than 10. Since we moved it to the right and we know that our number is smaller than 1, our exponent is going to be negative. 1, 2, 3. So that's just a little refresher if you didn't remember offhand and you didn't have time to flip back in your notes or something. So you will need to be able to express your answer in scientific notation. So that's going from atoms to moles and moles to atoms using Avogadro's number. Do we have any questions on that, or are we good to move on? All right, we'll keep moving ahead then. The next concept we're going to add on to the concept of the mole is molar mass. So if we have 1 mole of a substance, the mass of that substance, 1 mole of it, is the molar mass. So if I had 1 mole of carbon, I would have 12.01 grams per mole. Okay, that's the molar mass. We express molar mass as the number of grams in 1 mole of substance. The way that we figure this out is by looking at the periodic table. So you look at the periodic table, you find whatever elements are involved in the compound that you're trying to calculate a molar mass for. You add them all up, and there you go. And I think it's better to have an example than to just look at the words. So I'm going to do the first one for you, and then I want you to do the second one. So if I asked you what's the molar mass of magnesium sulfate, what you would do is go to your periodic table. You'd find magnesium, sulfur, and oxygen. You'd report the mass, which is the decimal number that's underneath the symbol. So if you have your periodic table, look up magnesium and tell me what the what the atomic mass is that's on the periodic table. Looking for magnesium. And I'm using the one that I put on Blackboard, so if that's the one you're using, we'll have the same numbers. So I'm going to go with the 24.305 just because that's what I have. But if you use 24.31, you're not going to be too far off. Okay. So I'm going to write that as grams per mole, because if we had 1 mole of magnesium, it would weigh 24.305 grams. You do the same thing for all the others. Now, oxygen is 15.999 grams per mole. It's okay to round to 16. But don't just arbitrarily round like, okay, 24.305 is 24. Don't do that. But oxygen, you can call that 16, okay? So we've got all of our information from the periodic table, but we still haven't answered the question of the molar mass of magnesium sulfate. How many magnesium atoms are in this compound, magnesium sulfate? There's one. Same thing for the sulfur. How many oxygens do we have? We've got 4 of them. So when we do this, we're going to add 24.035, or 305, excuse me, plus our 1 sulfur, plus 4 times what we had for oxygen, because there are 4 of them. So that's the magnesium, the sulfur, and the O4. When you add all that up and you take into account sig figs, which I'm not going to be too stringent on sig figs when it comes to molar mass. You should get something in the ballpark of 120.367 grams per mole. So we're finding all of the masses on the periodic table. And then you look at each element and you multiply that mass by the number that you have in your compound. So magnesium, we only had 1. Sulfur, we only had 1. But oxygen, we had 4. So we had to multiply that number by 4. We add all that up, and that's our molar mass, which I abbreviate MM. Give the second one a try. Find the molar mass of lead 2 chloride. I'll give you about a minute to do it, and then I'll check in with you. All right, I'm seeing a couple of answers that look good. So I'm going to show how we get there. In this compound, we've got 2 elements, lead and chlorine. When you look those up, lead is kind of heavy, 207.2 grams per mole. And chlorine, not so much, 35.453 grams per mole. We've only got 1 lead atom, but we've got 2 chlorine atoms. So we have to make sure to take that into account. When you add those together, you should get 278.106 grams per mole. Now, if we were doing strict sig figs, then we would do the adding thing, and we would only be able to report 1 decimal place. I'm not going to hold you to that for this. So as long as you get something in the ballpark, should be all right. And for the exam, we're all going to have the same exact periodic table. So there shouldn't be any questions as to, what exactly the molar the molar mass is. So are we good on molar mass? So we can use molar mass to go from moles to mass. If we can calculate the molar mass, which we always can if we know the formula for the compound, then we can figure out how much of it we have. So here's an example. What is the mass of 1.33 moles of titanium? So we've got moles, and we need to go to mass. For this type of a problem, you're always going to use molar mass. And I'm specifically writing down the problem types again because you need to be able to recognize these and know which piece of information to use for each type. And at the end, I'll fill in like kind of a cheat sheet for you to use. So we need to use molar mass. The only thing we're looking at is titanium. So what is the molar mass of titanium? Exactly. All you do is you look at the periodic table for titanium, and that's it. Reported as grams per mole. The other way that we can write that is as a unit factor. So that's the same thing. And that's actually the unit factor that we need. Does everybody see that? We're trying to go from moles to mass. So we need to use the molar mass to figure it out. That is our unit factor. But remember that we can also use the reciprocal to go in the opposite direction. So if you do this math, you should get 63.7 grams of titanium. And that makes sense. We have more than a mole, so we got a little bit more than the molar mass. So again, this is a mole to mass question, and we use molar mass. We're not going to stop there. No. We can combine these. So if we have the number of atoms, we could figure out the mass. If we had the mass, we can figure out the number of atoms. Because both of these numbers, Avogadro's number and the molar mass, are related to 1 mole of substance. So our unit factors I'm just using atoms here, but remember it can be molecules. In both of these cases, we're relating a number to 1 mole. So we can do multiple steps to figure out something as long as we convert to moles along the way. I'm going to show you an example of that. So are we ready to move to the next slide, or do you need another second to jot this down? I'll wait a second. And remember, I always post the PDF for this. You may not have access to a printer, or you may not want to print all of this, but you can always go back and fill in your notes too. But I'm happy to wait. Okay. So let's do a sample problem. What is the mass of 4.55 times 10 to the 23rd atoms of carbon? So we're going from atoms to mass. We can't just jump directly there. We've got to use moles as an intermediate. So whenever a question is asking you, okay, you have atoms, how many, what's the mass or how many grams? Or the reverse, you have to convert to moles first. So what this really is going from atoms to moles for part 1, and then going from moles to mass. Now this should look familiar because we did both of these simple problem types. We did atoms to moles using Avogadro's number. And to go from moles to mass, we used molar mass. So if we string those two calculations together, we can go from the number of atoms to the mass. Does that concept make sense for everybody? Because if this leap doesn't make sense, then the numbers aren't not going to help, okay? So let's start throwing some numbers out there. We need to put some unit factors together so that we can write this equation together. So for the first one, we're using Avogadro's number. And we're trying to go from atoms to moles. So should I put my atoms on top or on the bottom? Exactly. Atoms should go on the bottom. So wherever you put your atoms, that's where you're putting Avogadro's number. On top, we're going to put 1 mole of carbon. So that is our unit factor for that first part. What about the second part? Molar mass is in grams per mole. We're trying to go from moles to grams. Oh, can I explain why the atoms are going on the bottom? So we're trying to get rid of atoms. We need atoms to cancel out. So when we multiply the number of atoms of carbon we have by that, the 6.02, that's Avogadro's number. So Avogadro's number is the number of atoms in 1 mole of something. Yeah. So whenever you're doing atoms to moles, you're going to see that 6.02 times 10 to the 23rd. Always and forever. Did I explain well enough why that number goes on the bottom for you? Okay, good. You're welcome. So for the second part, we're going from moles to mass. And in this case, the mass is in grams. Where do I want to put those grams? Should they be in the top or should they be in the bottom? Because remember, the molar mass is just another unit factor. So grams in the top or grams in the bottom? We should put our grams in the top. Now this is carbon, so its molar mass, you just get it from the periodic table. So it's 12.01 grams per mole. To write our unit factor, it's going to be exactly that. We said grams in the top, 12.01 grams of carbon for every 1 mole of carbon. Now I'm going to do these in different colors. Let's see. So I'll write that one in blue. We're starting with the number of atoms. Then we're going to take those atoms and convert to the number of moles. Then we're going to take those moles and convert it to mass in grams. When you do this, I want you to try this in your calculator. You're going to put in the 4.55 times 10 to the 23rd. Divide by Avogadro's number. And then multiply by 12.01. Once you do that, you can throw your answer in the chat. But I want you to try it in your calculator because this is important. If you can't do it in your calculator, then you're going to be lost. You were close with that, though. 9.1. So with sig figs, it's 9.08, okay? And what we're using to determine the number of sig figs is the number of atoms. That's the given information. We don't use the molar mass like that, really. So always go back to the given information in the problem and use that. Are there any questions? Questions about your calculator, which I may or may not be able to answer just off the cuff without knowing your exact calculator, but you can still ask. or questions about how we strung these two calculations together. Yeah, if you're good, let me know, because I have a problem for you to try. Okay. Then I want y'all to try this one. Yes, it's the same number, but we've got a different molecule. We've got carbon dioxide. So what is the mass of 4.55 times 10 to the 23rd molecules of carbon dioxide? And then I put the chemical formula here just so that there's no ambiguity. So that's CO2. I'll give you 3 minutes and then I'll check back in. You can put your answer in the chat if you got one. And if you need help, you can say help too. So if you logged on late, then you missed some stuff. So this might be struggle bus. All right, so we got a couple of answers. Feel free to put it in the chat as I solve the problem. So it's the same type of problem, literally almost the exact same. We have the number of molecules, and we're trying to go to the mass. We can't jump straight from one to the other. We have to use moles. So we're going to go from molecules to moles, and then moles to mass. For the first one, we're going to use Avogadro's number this exact same way. And of course, my phone rings. My bad, y'all. Happens to us too. I forgot to put it on silent. So to go from molecules to moles, we're going to use Avogadro's number. To go from moles to mass, we're going to use the molar mass of carbon dioxide. For this, we actually had to do a little bit of work. So you have to look up carbon and oxygen and figure that out. What was the molar mass? If you got an answer, or if you got this far, what's the molar mass of carbon dioxide? Yeah, that looks about right. So I approximated here with 16 because 15.999 is kind of annoying to write. So 16 is just fine for oxygen. If you use 16, then you get 44.01 grams per mole. If you use the 15.999, then you'll get the 44.008. Either one is fine. Our unit factor for the first one is going to be exactly the same as the last problem. Either one. So I typically will approximate oxygen as 16 grams per mole. That's really the only thing that I approximate. Everything else I use exactly what it says on the periodic table. But when I'm grading your exams or your homework, I give a little bit of leeway for that, so it may differ by, zero point 0.1 or something like that in your answer. Not a big deal. So I have like a little window of tolerance for your answers. So don't be super concerned about that. So for our first unit factor, we're using Avogadro's number, and we're going to go from molecules to moles. So we're going to have moles on top and molecules in the bottom. Wherever the molecules or the atoms are, that's where you're putting Avogadro's number. To convert from moles to mass, we're going to use the molar mass. We're going to keep the grams on top and have moles on the bottom so that it cancels. When you put it all together, you start with the same number of molecules So that number is going to be exactly the same as the last problem. The number of moles of carbon and 4.55 times 10 to the 23rd atoms of carbon, same as the number of moles of CO2 for 4.55 times 10 to the 23rd molecules of CO2. So that's exactly the same. What's different is the molar mass. Always do your unit analysis to make sure that you're canceling out what you need to cancel out. And you need something on the top and on the bottom in order for it to cancel. In this case, we're left with grams of CO2, which is good because we're looking for the mass. With sig figs, it should be 33.3 grams of carbon dioxide. Don't forget your units, because I won't know what that 33.3 means, and you'll lose half a point just because of it. You'll also want to take into account significant figures for your final answer. Again, we only have the given number 4.55 times 10 to the 23rd, and that's 3 sig figs. So your answer should also have 3 sig figs. Are we good on that? Any questions? Now we're going to go from mass to moles, or molecules, excuse me. We have oxygen. This is oxygen gas. And we've got 2.25 grams of it. And the question is asking how many oxygen molecules are present. It's the same thing, just in reverse. Oops. I wrote it the wrong way. My bad, y'all. Said it right, wrote it wrong. So we're starting with the mass and converting that to moles using the molar mass of oxygen. The molar mass of oxygen is going to be 2 times 16 grams per mole, which is 32 grams per mole. That's why I like using 16 instead of 15.999, because I can do the math. Then we're going to take those moles and convert to molecules. What do we use to convert moles to molecules? Yep, we use Avogadro's number. Yeah, you can abbreviate it. Avogadro is kind of a mouthful. Makes me think of avocado, probably because I'm hungry because I didn't have breakfast this morning. But you can abbreviate and I'll get it. So I'll stick with kind of the same color scheme in terms of which one comes first. So the first unit factor is always going to be that blue color, and the second one is going to be purple. We're starting with 2.25 grams of oxygen gas. We're converting that to moles. What am I putting at the top of this unit factor? Yes, 1 mole. That's the answer. That's the question that lets me know if you get it. Because you can use that molar mass as a unit factor. And since we're trying to get rid of grams, the grams have to go on the bottom and the mole has to go on the top. So keep in mind that molar mass can be written in 2 ways. So that's the first part. And now we've got moles of oxygen. Oops. Now we're converting moles to molecules. Where am I going to put Avogadro's number? The top or the bottom? We're going to put it in the top. So what we're trying to keep, we're going to put in the top in this case. Because remember, we want moles to cancel. So if you can't remember where to put the number, think about what needs to cancel. And since we just figured out moles and we're going from moles to molecules, you got to cancel out the moles so that you can get to molecules. Does that help with figuring out what to put where? Good. So we're left with molecules. And you should get something in the ballpark of 4.23 times 10 to the 22nd oxygen molecules. Again, don't forget your units. So how we feel about these? Atoms to mass, or mass to atoms or molecules. We good on that problem type? Yeah, of course it'll be practice, but as long as you feel like could be able to try a problem with this example, that's where we're trying to be. You understand it enough to where you can look at an example and kind of recreate it for a new problem. So we're going to do this last problem and then we'll take a short break. This problem, we're looking at the mass of a single atom or molecule. What is the mass of a single molecule of sodium chloride, which is NaCl? Seems like a really hard problem, but it's not. At its very core, it's pretty much the same thing as a molecule to mass problem. Only instead of having a lot of molecules, we've just got one. A single molecule we can still convert it to the number of moles. And we're going to use Avogadro's number. And then we're going to use the molar mass. So the molar mass of NaCl you got to find sodium and chlorine. Yeah, it's in that ballpark. So if you're using a slightly different periodic table, then you might have slightly different answers. But very, very slight. So we've got our molar mass of sodium chloride. Now we're going to fill that in. And since we're trying to get grams at the end, then we're going to put grams at the top. And moles of NaCl at the bottom. When you do that math, you get a really tiny number. Clearly, you cannot measure that on any kind of a scale. And here in this type of problem, I would tell you how many sig figs to report. You will have a question like this on your exam, on exam 4, and on the final. So just word to the wise, I always give a problem like this. So know how to do this specific problem of calculating the mass of a single molecule or a single atom of something. Are there any questions? And let me know if this style works for you. So I teach this by example. I give you problem types, and then we do a bunch of them. We do them in reverse. I ask you questions along the way. If there's anything else that you think might help you, you can feel free to say it in the chat. You can send it in a private chat or course messages, anything like that. Because each class is different. Each person is different. I can't do everything for everybody, but I want to make sure everyone's kind of getting something for them. All right. So if we're okay, then I'm going to say we take a break until 9:30. Or not. Yes. So if you can't come to office hours on Wednesdays, because I know there were it was a close call in terms of when office hours are going to be amongst all my classes. But you can always send me a message through course messages and set up something else. So I'm kind of available on Wednesday, like 12 to 2 as well, for those of you who have class from 2 to 4:30. So just send me a message and we can work something out. No problem. So take a break till 9:30. Then we'll get back to it. It's 9:30. Time to get back to it. The break always feels shorter than it needs to be. But we've got about an hour left, so I think we can do it. So far, we've covered what a mole is and how to calculate moles from the number of atoms or molecules from the number of moles. We also talked about mass and moles, and we put those concepts together. Now we're going to add another concept, so another molar thing. Molar volume. This is only for gases. Gases at STP, which is standard temperature and pressure. At STP, 1 mole of any gas occupies 22.4 liters. That volume is called the molar volume. The conditions for that are 0 degrees Celsius and 1 atmosphere. Now, typically for gases, we're talking about Kelvin. Same thing. So 1 mole of gas has 6.02 times 10 to the 23rd molecules of that gas. And we know that from Avogadro's number. And we know that the volume of that gas at STP is going to be 22.4 liters. So that's molar volume. We good on that concept? This is where we see how many people are actually back on time from break. No. Okay. Do you have a specific question, Cameron? Or do you just need me to run it back? Okay. So we're talking about molar volume, which is only for gases at standard temperature and pressure, STP. Under these conditions, where the temperature is 273 Kelvin or 0 degrees Celsius, and 1 atmosphere of pressure, the volume of 1 mole of gas is 22.4 liters. So it could be oxygen gas, fluorine gas, whatever gas you can think of. 1 mole of it under STP conditions is going to take up a volume of 22.4 liters. So we can talk about a gas in 3 different ways. We can talk about the moles of gas. We can talk about the number of particles of gas, or molecules, using Avogadro's number. 1 mole of gas is the same as 6.02 times 10 to the 23rd molecules of gas. So it could be oxygen gas, fluorine gas, carbon dioxide, whatever. If you took those 6.02 times 10 to the 23rd molecules and you measured the volume that they took up at STP, the volume of that gas would be 22.4 liters. Does that second run through help you? You're welcome. So let's do an example problem with molar volume. A sample of propane occupies 4.50 liters at STP. How many moles of propane are present? Couple of things here. You'll know that you're dealing with something that requires molar volume or something specific to gas when you see liters or STP. You'll always see STP for these types of problems, okay? There's only one exception, and that's when we get to gases in chapter 10. But until then, don't worry about it. So if you see that something is at STP, automatically think gases. So that adds on molar volume to the things that you can use to do calculations. The type of problem that we're doing is we're going from a volume, 4.5 liters, to moles. So that's another problem type, volume to moles. We can do this directly. Whenever you're converting volume to moles or moles to volume at STP, you're going to use molar volume. So that is the unit equation. And yes, I'm bringing back up that chapter 2 terminology because we're getting close to the end and you'll need to remember it for the final exam. If that's the unit equation, then we can write unit factors. So these are the unit factors that we have to work with. We're trying to take the number of liters of gas and convert it to the number of moles. So which unit factor should I use? A or B? Y'all already know what I'm going to ask. Once you see me label them, just get your answer ready. And we should use the first one. We should use A. We're trying to cancel out those liters, so we need to put those in the bottom. When you do that math, you should get 0.201 moles of propane. Questions about this? If not, I have a problem for you to solve. So I want you to try this problem. You've got oxygen gas, and it occupies a volume of 6.85 liters. Calculate the number of moles. So just like what we did. I'll give you 2 minutes. If you have an answer, you can go ahead and put it in the chat. I'm going to start setting up the problem. So like I said before, it's the same type of problem that we just did. You're taking a volume and you're using the molar volume to convert to the number of moles. When you do that, you should get 0.306 moles of oxygen gas. So if we were doing the other way, where you had the number of moles and you had to calculate the volume, you would just flip this unit factor. So several of you got that answer, which is great. Are we ready to move on? All right. So when we're talking about gases, we can also talk about density. We talked about density in chapter 2. We were really talking about the density of, liquids and solids primarily. But gases, they have a density that's really small because those particles are kind of far apart. At STP, we can write the density as the molar mass in grams divided by the molar volume in liters. Because remember, density is equal to mass over volume. And if we assume that we have 1 mole of gas, then the mass of that 1 mole is going to be the molar mass. And the volume is going to be 22.4 liters, which is the molar volume. The other thing you're going to want to note is the units. We're in grams per liter. That's another way that you know you're talking about a gas. Again, it's my preference to show you what this means through a problem. So if this doesn't make sense just by seeing it on the slide, hopefully doing a sample problem will help sort that out for you. What is the density of propane gas at STP? We know that density in general is mass divided by volume. At STP, it's the molar mass, which I abbreviate MM, over the molar volume, MV. Our molar mass we can calculate. So take a second and calculate the molar mass of propane. I'm going to start writing it out here. So we've got 3 carbons and we've got 8 hydrogens. So it should be somewhere in the ballpark of 44, just a hair over 44 grams per mole. So when we're calculating our density, we've got our molar mass that we can just report in grams. The molar volume we're going to use is at 22.4 liters, because at STP, that's what the volume of 1 mole is. When you do that division, you should get something like 1.97 grams per mole. And in a problem like this, I would tell you how many significant figures to report. Does the density concept make sense with gases? We're going to do one more problem with density. And I'm going to walk you through this one too. We've got an unknown gas with a mass of 2.36 grams, and it occupies 1.50 liters at STP. calculate the molar mass of the gas. This is where you need to know both definitions of density. No matter what you have, solid, liquid, or gas, the density of it will always be the mass divided by the volume. We're being asked about the molar mass of the gas, and it seems like we wouldn't be able to figure that out. But we can, because we can figure out what the density is. So this is step 1, using the mass and the volume that we're given to calculate the density. When you do that, you should get a density something like that. Now, I didn't round this answer simply because this isn't the end. So I want to keep a few extra digits. So this is the density of the gas. The question is asking about molar mass, though. Well, we know another definition of density, which includes molar mass and molar volume. If we assume that we have 1 mole of gas, then we can use the molar mass over molar volume equation. We already know what the density is, and that's in grams per liter. So we can solve for the molar mass. All you have to do here is multiply both sides by 22.4 liters. You will have a problem like this on your exam. So I'll give you a second to digest it and let me know if you have questions about the 2 different steps that we had to do. Are there questions about this one? Or let me know if you're ready to move on. Yes, that's exactly what you do. You figure out the density using the information given, which was the mass and the volume. And then you say that density is equal to the molar mass over the molar volume, assuming that you have 1 mole of your gas. No problem. Other questions, or let me know if you're ready to move on. Yes, molar volume is always 22.4 liters. It's just like Avogadro's number is always 6.02 times 10 to the 23rd. So those are two numbers that you will need to know. Alrighty, let's move on. So let's do a little bit of summary. We've got three different interpretations for the mole. We've got Avogadro's number, and that gets us from moles to atoms or molecules, and the reverse. We've got molar mass, which tells us about mass in grams. And then we've got this special case for gases, where 1 mole of gas at STP is 22.4 liters. So just like how earlier we combined some of these different interpretations to go from the number of atoms to, say, the mass of those atoms, or the reverse, we can do the same thing with all of these. So here's a sample question that I want you to take a stab at. I'll get you started a little bit. We've got how many molecules of xenon gas occupy 0.430 liters at STP. We're starting with a volume. We're trying to get to the number of molecules. We can't really just make that jump. So you're going to go from volume to moles, and then moles to molecules. So that's the hint I'll give you. And I'll give you 3 minutes to give this a shot. Then I'll start solving the problem. If you get stuck, you can say stuck or help. So just because you don't have an answer doesn't mean that you can't participate. If you let me know that you're stuck, that gives me an idea of where you are, and I can change up how I explain it. I can kind of iron things out in a little bit more clearer detail, all that sort of stuff. So if you're stuck or you need help, let me know, because I can't help you if I don't know. Okay, 3 minutes. All right, how are we doing with the problem? If you have an answer, you can go ahead and put it in the chat. Okay, if you're stuck, yeah, let me know if you're stuck. Yes, the second unit factor is Avogadro's number. So let's start going over it. Whenever we're talking about gases and volume, you're going to use molar volume. We know that 1 mole of gas has a volume of 22.4 liters. To go from moles to molecules, we're going to use Avogadro's number. We're trying to get rid of liters and get to moles. So that 22.4 liters, is that going to go in the top or the bottom for our unit factor? It's going to go on the bottom. In the top, we're going to put 1 mole of xenon. For our second unit factor, we're taking moles and converting to molecules. We're using Avogadro's number here. Where do I put his number? The top or the bottom? And we're going to put his number at the top. So those are our 2 unit factors. Now we need to put the equation together. We're starting with a volume of gas. We're trying to get to moles. We're getting there. We put in our second unit factor. Didn't leave enough room to write the word molecules, but that's okay. So if you didn't get a chance to, if you didn't get this far, take a second and put this in your calculator. So you should get 1.16 times 10 to the 22nd. So you always want to include that that exponent, because that's a big difference. It doesn't matter if you put Xe molecules or molecules of Xe. Either one. So how do we feel about that one? It's going to take some practice. But once you can identify the type of problem it is and know which unit factors to use, that's like 2/3 of the problem right there. Then it's just figuring out the numbers. Let's do some more. What is the mass of 3.36 liters of nitrogen gas at STP? So this one, we've got a volume, or we're trying to get to a mass. Anytime you see volume, liters, or you see STP, it means you're dealing with a gas. So you will likely have to use molar volume at some point. The first thing you're going to do is take that volume and convert it to moles the same way we did before. That's with the molar volume. And we say that 1 mole of gas has the volume of 22.4 liters. Now we've got to go from moles to mass. Anybody remember how we do that? Give you a hint, it's got mass in the name. Molar mass. So when we're going from moles to mass or mass to moles, you've got to use molar mass. We've got nitrogen gas here. And I always like to calculate my molar mass before I start doing the unit factors. That's just my preference. Yep. So we've got our molar mass for nitrogen gas. Now we can start writing out the problem. And I kind of flip back and forth between writing out the unit factors first and just putting the whole problem together. That's kind of by design because some people like to do it one way and some like to do it the other. So this time we're just going to write out the whole equation. This time we're starting with the volume. And just like before, we're converting it to moles. So we're going to put the volume on the bottom, the molar volume that is, and 1 mole of nitrogen at the top. That will take us from liters to moles. Now we've got to go from moles to mass. We're going to put the number of grams in the top. And the reason for that is that's what we want to end up with at the end. And we have to cancel out those moles of nitrogen. So if we go through and do our unit analysis, you get rid of the liters, and you're left with moles. Then you get rid of moles, and you're left with grams. Take a minute and put that in your calculator and let me know what you get. With sig figs, it should be 4.20 grams of nitrogen gas. So does that leap make sense? To go from volume to mass, we went from volume to moles first, using the molar volume. Then we used the molar mass of nitrogen gas to go from moles to the number of grams. All right. So this is the cheat sheet I was telling you about. I'm going to fill some stuff in for you here. This may be one of those things that you might want to print out and put in your notebook, or you can just fill it in your notes right now. But I kind of have a head start. So what you already see listed here are the different problem types that we did. I'm going to label them now. So I'm labeling them A and B because I have the forward and reverse. So they're kind of like pairs. For example, 1A is moles to atoms or molecules. The reverse of that is the B, atoms or molecules to moles. To go from moles to atoms or molecules, we're going to use Avogadro's number. And that's true for both of these. But the unit factor you use is going to be different. In the first case, where you're trying to go from moles to the number of atoms, you're going to put Avogadro's number at the top. If you're trying to go from atoms or molecules to moles, you're going to reverse that. You're going to flip it upside down. And this is simply going over what we did in class. So hopefully this will help you bring everything together. The second problem type we did was moles to mass and mass to moles. You will always use molar mass. And that's something that you're going to have to calculate unless it's given in the problem. So remember, to do that, you just total up all of the masses that you see on the periodic table for the elements that you see in the compound. If you're trying to convert from the number of moles to the mass, you're going to have your grams of substance on top and 1 mole of substance on the bottom. And that will get rid of the moles and leave you with grams. If you're trying to take a mass and go to moles, you flip that upside down. You're going to put the moles on top and the grams on the bottom. The final type that we did, and this is excluding density. Density is a problem type, but it's not exactly the same. So don't forget about density, y'all. The third problem type that we're going to have on our cheat sheet is moles to volume and volume to moles. Note that it's only for gas and it's at STP. That will become important when we start doing gas laws where things can change. For these problems in Chapter 8, we're always going to use molar volume. To convert from moles to volume, you're going to put that 22.4 liters on the top and 1 mole on the bottom. That will cancel out your moles and leave you with liters. If you're trying to go in the opposite direction, take a volume and convert to moles, then you'll put the moles in the top and the 22.4 liters in the bottom. So this summarizes the majority of what we did today. The only exception is we didn't cover density in here. But as you can see, I can't fit it. So density is kind of its own little thing. Let me know if you need another couple of minutes to get this written down. Or just let me know when you're ready. All right, we say ready, I'm going to move on. So speak now or forever hold your peace. I mean, you can always go back to it, but, you know. Okay. So some reminders for you. Midterm grades, I have to submit this week. So everything up through chapter 7, so the Mastering Chemistry chapter 7, is going to be included. Now, if, you were sick or something and, there's some other things, like, obviously I'm not going to do that to you. But keep in mind, if you've been here the whole time, your midterm grade is going to reflect everything we've done up to this point. So exams 1 through 3, all the chapter check-ins, and the Mastering Chemistry assignments up through chapter 7. That's what your midterm grade is going to reflect. That is the bulk of the class. I'm going to be updating grades and entering those grades like Wednesday, Thursday. So you'll be able to check Blackboard and see what your grade is, which is actually pretty close. So I think I just have one more assignment to catch up on. So if you looked at your grade now, that's pretty representative of what it's going to be. If you're not happy with that, you need to make an appointment with me and we can talk about it. I do not give extra credit assignments like to individual people. I make extra credit available to everyone. So don't ask me, okay? Don't at me. Don't ask me. It ain't gonna happen. You're gonna have a chapter 8 check-in due this Sunday, which is a little bit different from the syllabus. I want to do a check-in so that you can try a couple of these problem types on your own, and I can try to take a look at them, and we can review the parts that we covered today that still didn't stick, so we can do some more problems next week and finish covering chapter 8. Your chapter 8 Mastering Chemistry is due on the 25th. So not this coming Sunday, the Sunday after that. So after we cover the rest of chapter 8 next week, then you'll be able to wrap up that assignment and have it done. Don't leave it until next week. Please, please, please. Try the homework. Try the problems that look like ones that we've done, and then come with questions, either to office hours or class on Monday. The last exam in this class is exam 4, and it covers chapters 7 and 8. So make sure that you're ready.